Whoa! What? Hi, I'm Ara, N6ARA, and welcome to part 2 of the TinyGawant series. Now, if you haven't seen part 1, that's fine. I have a link to it as a card above and in the description below, so definitely go check that out. But as a quick recap, in episode 1, we went through the process of building this Gawant antenna that we're calling the TinyGawant. It's the first revision, so Rev A, and I talk about the design process, the theory of operation, how we built it, and eventually did a field test where we checked to see if this antenna would even work. The good news is the antenna totally worked, and we learned a lot about it, and even thought of some design improvements we can make for the Rev B model, which is what we're going to cover in this episode. So with that said, let's dive into those design improvements. Last time I noted 2 improvements that we could make to this design. The first one is an LED indicator to show us when we are close to a SWR of, say, 2:1 or less, somewhere where it's safe to operate this antenna. The second idea is to consolidate these 2 build variants into one. Right now, if you wish to operate the 20 to 10 meter band, you need 12 turns on the toroid, and if you wish to operate the 40 to 20 meter band, you actually need 25. The only difference between these two is this one has 13 more turns than that one. So why not just add a switch that lets you add those turns or remove them based on which bands you want to operate on? That way you have one Gawant to rule them all. With those 2 improvements in mind, let's start with the easiest one first, the band switch. To add this capability, we take the original design where we have 2 turns at the primary and 25 turns at the secondary, and add a tap at the 12th turn along with a single pole double throw switch that lets us choose how many secondary turns we want to pass onward towards the parallel cap and antenna. So for 20 meter band operation, you select 25 turns, and for 10 to 20 meter band, you select 12 turns. The only custom work I really had to do here was updating the transformer footprint to have an extra tap. Next is the SWR indicator. This one, though, is a little more tricky. First, I thought about implementing a proper dual directional coupler to indicate forward and reverse power, but figured this would add 2 more toroids to the design, drive up cost, and sort of complicate things since not everybody likes to wind toroids. Plus, it makes the volume that this whole device takes up a little bit bigger. Now, I could dive into how dual directional couplers work in this video, but frankly, that in itself is a whole nother video, and in fact, Alan, W2AEW, has an excellent video on how this circuit works, and I've actually linked that in the description below if you're interested. Anyway, after thinking about it some more, I realized that the dual directional coupler is probably not the best fit, and my next thought was, well, why not just reuse the mini SWR meter design I already have, right? It's got 1 toroid instead of 2, so fewer parts. And the nice thing is it's got an LED to indicate forward power and 3 LEDs to indicate SWR ranging from 1:1 all the way to 3:1. And when you look at the design itself, it's got a few diodes and LEDs, some resistors, and even a variable resistor to calibrate and tune the circuit. But this is kind of a bit of overkill for the TinyGawant, right? If we're trying to keep the cost down and the part count down, the minimum viable product here is really just 1 LED to indicate whether you're above 2:1 or below it to tell you if it's safe to operate the antenna or not. So this design's good and we could use it, but I really wanted to try finding something a little bit simpler. And it doesn't get any simpler than this, the resistive SWR bridge. This design has no toroids and can be easily implemented to indicate when the SWR is above or below a certain threshold using an LED indicator. Now, the downside to this design is that it's a little power hungry. And so what you typically see is that most folks will implement a switch that lets them bypass the SWR bridge once they've got it all tuned up, and that way you don't dissipate a bunch of power into it. Now, before we go ahead and implement this in KiCad, let's first try to understand a little bit about the circuit diagram and how it works. Now, I'll admit, I didn't understand how this circuit worked the first time I saw it, and it took me a few iterations of redrawing it and thinking through all the signals and what's going on until it clicked for me. So let's redraw this, and I think it'll make a little bit more sense. Okay, so I've redrawn the circuit here a little such that the RF source enters the circuit from the top and the current then flows down both these branches. On the right side branch, the signal sees a voltage divider set by these two 50 ohm resistors. So the signal here at this node will always be half of the voltage at the source. On the left-hand side, you also have a voltage divider with a fixed 50 ohm resistor on top, but the bottom you have your RF output, which goes to the antenna or your RF load. Now, depending on the load presented at the output, the voltage here at this node will vary, right? So if you, say for example, had a 50 ohm load, right, a 1-to-1 SWR match, the voltage here would be exactly half of that of the voltage at the source, just like this other side. And so the difference between these two nodes here would be 0 volts. At least with the way the circuit works, the LED, when the difference between these two ends is 0, results in the LED not turning on. And the LED not turning on then indicates a good match. However, if you start to increase the resistance at the load, starting to drive the SWR up, the voltage at this node will begin to increase as a result. And so the differential voltage now between these two nodes will also increase. Now you may be looking at this and thinking, hey, this looks familiar, and you'd be right. This is essentially a Wheatstone bridge, and the added trick here is that we've installed a peak detector between the Wheatstone bridge to illuminate the LED when the differential voltage has crossed a certain threshold set by this resistor and Zener diode. So if you dial these two components right, you can actually get this LED to light up when the SWR is above 2-to-1. And once the SWR drops low enough, the LED will then extinguish. Now keep in mind, this LED isn't going to just turn on and off like a switch. It's actually going to gradually dim and brighten as we cross that 2-to-1 SWR threshold. But honestly, that's good enough for this application. And now that I think we understand a little bit more about this circuit, let's go implement it in KiCad and see if it works. And here's a KiCad schematic. So here we have our RF input feeding into a double pole, double throw switch that allows us to either bypass the SWR meter or put it in circuit to measure and allow us to tune the variable capacitor until this LED here dims and turns off. Once that happens, we can then set the switch back and bypass it for operation. And just one thing to note here is that these two components are actually really just one double pole, double throw switch, but schematically it's broken up like this so you can see how you can either bypass it or put the SWR meter in circuit. Okay, on to the layout. So I had to nudge around a bunch of these bigger components to make some additional room for the SWR circuit, but I managed to fit it all on one layer, and that freed up space on the front panel at least to host the tune and operate switch and the band select switch that lets you choose between 20 to 10 meter and 40 to 20 meter. Looking at our board in the 3D view, we can see the band select switch and our tune and operate switch as well, and our SWR indicator light, which in fact is mounted on the other side of the PCB, and there's this hole cut out here to allow light to illuminate through the cavity. In general, I found this technique actually works really well in daylight. Otherwise, if I put this LED on the front, it's a little tough to see under sunlight, but by recessing it in here, it really does help users see if the light is on or not. Now, looking at the back side, some of these components, I'm not going to lie, they're kind of close to one another, and I'm going to have to build it and see if it all fits. It's going to be pretty tight with the large components, but with these smaller components, I'm really not too worried. I'm going to probably solder these first, so I can get the solder iron in there to solder everything down and then tackle the big components once that's done. But in general, I'm really happy with this design. I think it's time to send it to the board house and see how it turns out. Let's go. And here it is. So the board looks really great. I inspected it under the microscope. All the traces and pads look textbook. Now, normally what I would do is I would show you the entire build process of this, but I think I covered it fairly well in the first video. So what I think I'll do instead is just show you what the differences are between this build and the previous. The first major difference is going to be the toroid. In this build, what we want to do is wrap 12 turns and then create a tap and then return back to the toroid to finish 13 more turns to make 25 total all the way around. So let's do that first. Okay, so we're at the 12th turn now. And so what we'll do is we'll make a fairly long one. We got a good bit of wire here. So I'm gonna fold it back on itself and then twist it a whole bunch. Okay, that's good enough. I don't know how much I'm going to need, so I gave myself way more than I will possibly need. Hopefully I'm not going to eat my words there. And 25. Okay, so our secondary winding starts here. We do 12 turns to the tap, and then continue for 13 more to make a total of 25 turns all the way around. The second thing that differs in this build is that we have some surface mount parts here to install for the SWR meter. Most of these parts are large enough that you can just solder without a microscope. I usually like to use one just because it's nice to inspect the solder joints, but you know, large components such as the 50 ohm resistors, those are fairly easy to solder by hand with just your eyeballs. So let's solder those on. My technique here is usually to put on some solder on one pad first. And then once you've got some solder on there, you can pick up the component and get one of the sides on. Once you have one side tacked down, you just simply tack down the other. All right, with the other side tacked down, the component is installed now, and then you just essentially repeat this process for the rest of the components. You just got to make sure that the diode and the LED here are in the correct polarity based on what the silkscreen says. Now I could show you a time lapse of me building this whole thing, but we've got a lot to cover, so let's just use some movie magic. Parts, toroid, variable capacitor, abracadabra. Wow, that was so easy. I wish all my soldering was like that. Now I'll admit, I originally forgot to include the Zener diode in the schematic and ended up having to cut a trace here and install it in a sort of janky way, but I think this should work. Okay, with the unit completely assembled now, all we need to do is install the case and give this thing a try. I should note here that I actually added a little slot in the housing here to let the user actually switch the switch here. Otherwise, the case would actually interfere with being able to do that. And in fact, as a result of putting this switch here, it actually moved this ground lug as well. So I had to modify a little bit of the casing, but for the most part, it's the exact same thing we had before in the Rev A model. Okay, with all this built up, let's hook it up to the SWR meter and see if it'll tune up. Okay, so we have the TinyGawant now with the whip antenna installed and fully extended out, connected to the Rig Expert SWR meter. What I think I'm going to do first is set the switch to the 20 to 10 meter position and check the dial, make sure it all tunes up across those bands, then switch to the 40 to 20 meter band select position and check that as well. Now, one thing to note here is that the tune and operate switch right now is set to tune, but you know, this SWR meter has nowhere near enough power to actually illuminate that LED. So I'm going to set it to the operate position for now, just to check that the transformer in this thing actually works the way I expect. Once we're done with that, we'll hook it up to a radio and we'll see if we can actually dial the SWR in using only the LED indicator. Let's give it a try. Hey, looking pretty good. It's got a 1.14 at its minimum, so I would say the 20 meter band side is working. Let's go all the way to the 10 meter side and see if that works as well. Hey, all right, 1.06 to 1 on 10 meter. So we know at least the 20 to 10 meter band is working. Let's now switch over to the 40 to 20 meter band selection and check 40 and 20. And we'd assume everything in the middle would tune up as well. All right, I'm getting 1.5 to 1 on the 20 meter band, so we can at least pick up where we left off in the previous band selection. So let's try 40 meter now and see if that tunes up. Okay, not bad. 1.6 to 1. You know, it's a little close to 2, but I'll take it. That's good enough to operate on most radios. So this band select switch totally works. That's great. All right, so next let's try testing the SWR LED indicator. I'm really curious to see if that resistive SWR bridge circuit works as expected. So let's get a radio, hook this up, and tune around and see if we can use that without having the need for a separate SWR meter. All right, so we're going to use my KX2 as the reference radio to test against the SWR LED indicator since it has a built-in SWR meter here. I've set the power output to 5 watts because I don't think this thing can handle more than that, so I don't really want to push it. I've switched to the 20 meter band to start with, and then we'll try the 40 meter after that. I'm actually going to turn off some of the lights around here so you can actually see the LED as it illuminates. Hey, all right. So I'm getting a high SWR, above 3 to 1 at least, and the LED is illuminating, so it's doing half the function, right? Let's see if it actually turns off when you get close to 2 to 1 and below. Oh, you can hear the antenna get in resonance. Turn down the volume a little bit for my own sanity. Ooh, that LED is nice and weak now. Looks like we're pretty close, and the KX2 is still reporting a fairly high SWR, so let's dial around a little more. Okay, so I can't get the LED to really turn off. It does dim quite a bit, but the KX2 is still reporting a fairly high SWR, so that's not a great sign. Let's try switching this from the 40 to 20 meter band selection to the 20 to 10 meter band selection to see if that makes any difference. Oh. Interesting, so the LED is turned off. I'm still getting a fairly high SWR here. What? Okay, well, let's switch to operate. Maybe that's messing with this. Nope. So the KX2 keeps reporting a high SWR, but the LED here has turned off completely, so I wonder what's wrong. Oh my gosh. Oh my gosh, ATU has been on this whole time. Oh, okay, well, this isn't good, because now I'm a little worried that with the ATU engaged, from whatever my last setting was, that I may have damaged something in this antenna, because when you have the ATU enabled, it assumes that the impedance at this BNC connector could be much higher than 50 ohms, right? Because you might have like an NFET hooked up or just a random wire. And so the ATU is going to add and remove capacitance and inductance to match the presented impedance at the output of the radio. So I'm just going to hope that I didn't do any damage to this thing and switch this thing into bypass mode. That was totally a dumb move on my part. I should have checked that. Okay, so the radio is now in bypass mode and is bypassing the automatic tuner inside the KX2. And so in theory, this should now give us a correct SWR reading. And hopefully I haven't fried this little LED circuit in here. So let's give it a try. Hey, all right, that's promising. LED is not turning on, the LED here is not turning on, which indicates a low SWR. I'm seeing 5 watts leaving the KX2, and the KX2 is also reporting a near 1-to-1 match. So this is good. Let's try detuning it and see if the SWR jumps up. Oh, interesting. The KX2 is seeing a low SWR, but the LED turns on. And I think that's because we've essentially presented the output of this with those 50 ohm voltage dividers. So, you know, there's some added impedance here from the SWR circuit itself. So that's kind of mucking with these values here. So I'm not going to trust that too much until we switch back to the operate mode on this switch. But the LED is now telling us, hey, your SWR is way too high. And I think if we switch to operate mode and do that again, yep, there it is. SWR is being reported as above 3-to-1. So, okay, I think this SWR bridge circuit is actually working as expected. I'm going to just quickly check it on the other bands to make sure it's not a fluke. All right, so now we're on the 10 meter band, and I've been tuning around a little bit, and I think I've got the LED to dim as I can get it. Still a little, you can still see it, but of course the SWR meter in the KX2 is reporting a good impedance because of the circuit I mentioned earlier sort of mucking with those values. But if I put into operate mode, we're bypassing the resistive SWR bridge, so we're directly going into the antenna circuit now after tuning it up. You know, the KX2 is reporting below 2-to-1, so I think that's good enough to use. So it looks like the 10 meter band works, the 20 meter band works. Let's just check the 40 and assume that everything in between will work as well. So switching to the 40 to 20 meter band selection, go back into tune mode. I think 40 meters is somewhere up here. Change the band on the KX2 to 40. Okay, well, that's about as dim as I'm going to be able to get it. Let's see if this thing is actually tuned up. All right, it looks like it's a little bit above 2-to-1. So the 40 meter band isn't all that great. It looks like if you can get the LED to dim just a little bit, even if it's still a little visible, your SWR is probably going to be somewhere around 2-to-1 or below. However, on the 40 meter band, you know, I cannot get it to completely dim and report a near 1-to-1, which, as we saw on the SWR meter earlier with the Rig Expert, it had a fairly high SWR to begin with, so I don't think it's going to get much better than that. For now, I think this is good enough to at least take out into the field and test with and see how this LED performs in the sunlight. Can we actually get it to tune? And how does the band selection work? How does the antenna perform? There's lots to test. I think this is worth taking out into the field already, and I'm sure we'll learn a lot. So let's go do that. Good morning. It's a snowy day here in the Los Padres National Forest. I'm on my way up to Mount Pinos with the Rev B TinyGawant in my backpack. I'm excited to be hiking in snow, like proper snow this time, like real proper snow. That's the tap test of, is it snow, is it not snow? So last time it was all about, will the Gawant antenna even work? And it did. This time it's about how well is it going to work, and have the features we've added, are they useful? I'm excited to give it a try. Let's see how it does. I knew I had made it to the top of the summit because there was no more up left to go. Summit! All right, let's get set up. All right, so I brought 2 radios today, not just one. The first radio we're going to try out, since we tried it out last time and it worked, is the QMX. I haven't changed anything about this kit. It's exactly the same, other than the fact that instead of using the Rev A version of the TinyGawant, today we're using the Rev B. So that would be the only change with this entire kit. The other radio I decided to bring today is the CFT1 by KM4 CFT Jonathan. He actually pointed out that this radio is very similar to the QMX and would be a great candidate for testing the next revision of the TinyGawant. In fact, it doesn't have a integrated SWR meter, and so the SWR meter we added to the TinyGawant would pair perfectly with this. So we're going to give this a try as well. Okay, so we got our QMX, a talent cell battery, the Tiny Paddle, and the Rev B version of the TinyGawant. So just like last time, it's as simple as taking the whip antenna, screwing it onto the antenna port, deploying the whip, and it's ready to go. Let's put this kit together. Okay, so that should be about it. It's so simple and easy to set up. It's almost too easy. So the first thing we're going to want to do is switch the Gawant into tune mode. That allows us to see the SWR LED extinguish when the SWR is like roughly below 2:1. We also need to set the band select to the 20 and 10 meter selection, since we're going to be starting on 15, and then I'm going to work around the bands and see how it does. So, all right, let's get started. Okay, so I was able to peak the noise floor with the dial, but figured I should move closer so you can actually see the SWR LED. Under direct sunlight, it's a little hard to see, but I think we can kind of shade it with the camera here, and you can see it as I tune around. So somewhere around here is the 15 meter band. So if I tap the DAW, you can see the LED lighting up. I'll bring it a little closer just in case you can't, but we're definitely too high, so let's try dialing it a little bit this way. Oh, okay, so LED is going down. The LED brightness is going down. Let's keep going a little bit more. Up, overshot. Let's go back a little. Oh yeah, that's now barely lighting up. I think we're on the money. We got a good SWR. All right, now let's switch it back to operator mode, and we're good to get on the air. Summit to summit. Whew, that's loud. Oh, there's DJ. We're getting an accurate signal report now. All right, to be complete, we're going to try 20 meter on the QMX and see how that does. That's the last band we haven't tried that this radio will support. You're not gonna be able to see it, but I'm gonna dial it until the LED extinguishes. All right, cool. LED's gone. Let's put it back into operation mode and start calling CQ. Pretty good. Okay, so we're all done testing the QMX. Now it's time to move on to the CFT1 and see how that does. So I've got the whole kit together. I have the CFT1, just like how we had it on the QMX. I have the tiny paddle connected to the paddle port, so I can send CW that way. Audio for headphones, and power brick is the 12-volt talent cell. I'm really excited to give this thing a try. Okay, so we're going to start on the 20 meter band. I usually like to dial up roughly to where I think the 20 meter band starts. We're going to go again to operate so we can listen a little better. We'll go to the FT8 region, somewhere around here. Oh, there we go. Oh yeah, you could definitely hear that. All right, close enough. Now I'm going to go to tune to test this. Oh my gosh, it's perfect. The LED's not even lighting up, so looks like I got close enough. So let's get on the air. We're going to switch back to operate and start calling CQ. So I'm not getting a whole lot more contacts now. I think it's because most of my usual chasers have already chased me on the QMX, so I'm not getting as many this time on the CFT1. Gonna pack it up for now, sort of running out of time for the day, but it was a successful test, I would say. Let's get going. Okay. That was the stupidest way to enter the scene. Definitely not going to keep that. Okay, so we're back at the lab now, and the test you just watched actually occurred a couple weeks ago. I just got busy and haven't had the chance to dig through the footage, but I'm picking it up again. And while reviewing this footage, trying to see what worked, what didn't work, I noticed a couple things. The first thing is that the Rev B model didn't really break any functionality that we had with the Rev A model. So we haven't really regressed in capabilities, which is always a good thing. The second thing I noticed is that the LED indicator, while a little tough to film, actually in person worked very remarkably well. And we are definitely keeping that feature. It's just a great thing to have, and it made the tuning way easier. The third thing I noticed is that I haven't really covered the 10 to 12 meter band range, and that's mostly because the radios I've been testing with just don't have those band capabilities, but it is something we're going to try out a little bit later. Now, one thing I forgot to record during this field test is the 30 to 40 meter band operation. I could have sworn the camera was rolling, but I dug through all my footage and just could not find it. But frankly, the footage is kind of boring because it's literally me calling CQ for 15 minutes straight and nobody answering. RBN got 0 hits, which makes me suspect that this antenna does not work on the 30 to 40 meter bands. In the previous video, I alluded to this counterpoise issue, but didn't really give a whole lot of details, and that's what I want to dive into next, because I think that might actually be the reason why the antenna is not working on the 30 to 40 meter band. So let's dive into that. Looking at the TinyGawant schematic again, my good friend and ham radio wizard Dan, AI6XG, pointed out that the ground of the primary side and the ground of the secondary side are actually tied together here. This means the RF source in this episode, the QMX and CFT1, and the operator holding the rig are actually part of the counterpoise network. To get more consistent and controlled results, we could try to cut the ground connection here and essentially force all of the returning RF current to leave through whatever counterpoise wire we install on the ground lug, instead of it splitting across the operator who's acting part of the counterpoise here and the actual counterpoise wire we want to use. The hope is that all the RF current flowing across this counterpoise wire will actually radiate out, specifically on the 30 to 40 meter bands where the whip is far too short and inefficient to work. Now, how do we actually practically achieve this? The board's already been built, so we're going to have to modify it. Thankfully, the layout is relatively simple. All we need to do is cut this big trace here, as well as cut this little sneak trace here going to the secondary side ground, and instead we will route it to the primary side ground, fully isolating the primary and secondary grounds from each other. So let's grab an X-Acto knife and get to work. Okay, so we got the patient on the operating table here and scalpel ready to go, but it looks like the trace I want to cut and remove is actually under this toroid. So I'm going to need to desolder these pads here and lift the toroid up if I'm going to be able to access and cut that trace. Otherwise, to cut the trace for the LED, that shouldn't be too hard. I've got reasonable access there, so I'll do that second. So I started by removing the secondary windings and the primary after that to give myself access to the trace I need to cut. After cutting the trace, it was all about just wiggling it back and forth until I could kind of peel it back like an orange and finally cut it at the end and remove the trace altogether. Then it was onto the little sneaky trace that I needed to cut. This was a little tougher to do, but it wasn't too bad. Just required a little bit of patience. And once I was done, essentially repeating the same steps as that larger trace, it was all about just cleaning it up and prepping it for rework. Now, as for the rework, all this really required me to do was get a 30 gauge Canar wire and run it from the ground of the LED to the primary ground that I mentioned before. Now, in order to finish all these steps, all I had to do was tack on the secondary windings first, and then get the primary on there, and then finish it up with putting the ground of the LED onto the primary ground. All right, I have my TinyGawant now reworked and hooked up to the Rig Expert. And what we're going to do next is we're going to check the SWR across all the bands without a counterpoise and then with a short and long counterpoise and see how it performs. At least from an SWR perspective, it's not really going to tell us a whole lot about how it's going to perform as an antenna, but at least this will give us some ballpark measurements that we can use and work off of. Now, instead of showing you the entire process, we're going to sweep through the frequencies, and I'm just going to go very quickly here and just jog through it with a time lapse and show you the final results as a chart. So the results here are really interesting, and I'll even say somewhat unexpected. This plot shows SWR as a function of frequency in megahertz, and to define the maximum usable SWR, I've drawn a dotted yellow line at the 2:1 SWR threshold. It's somewhat arbitrary, but I had to pick something that I'd be comfortable with using across all the radios I have. Looking at the data I gathered, it appears as though isolating the primary and secondary grounds made little difference to the overall SWR. Furthermore, adding a counterpoise appears to only hurt the SWR at the higher bands, but it almost made no difference at the lower bands. That said, this doesn't really tell us anything about how the antenna will radiate at the lower bands, just that it'll tune. And mind you, this data was gathered indoors, so the ground properties are not representative of the ground in the field. I think the next step here is to run outside and quickly test this design change, perhaps on a summit to give us the best odds. Alright, so I've brought the TinyGawant and my KX2 up to this local drive-up summit, and it's somehow raining right now. Not the usual weather we have around here, but I'm going to take this opportunity to quickly get set up and get on the air and get down as soon as possible because all my gear is getting soaked. So I brought all the versions of the TinyGawant I've built so far, but what we're going to focus on is testing the Rev B to see if breaking that primary secondary ground and isolating them and having a counterpoise will actually make this antenna radiate on the 30 to 40 meter band. All right, so I brought my 33-foot counterpoise. We're going to hook that up to the TinyGawant and get this thing tuned up and start calling CQ, see who comes back to us. Oh gosh, I made it worse. Hey, okay. So I got about an SWR of 2:1, at least reported by the KX2, but 5 watts leaving the radio. Conditions may be a bit crummy, but frankly, I should get at least one person. You can't see it, but the entire LA basin is through those clouds, so there's gotta be someone with 40 meter out there. Okay, so this part here is boring. Let's just time lapse through it. Spoiler alert, no one replied. Nope. I've also got no hits on RBN so far, so this is not looking too good. I will say the bands sound pretty rough, so it could also be the bands, but we should be getting at least spotted on the RBN with some local listening beacon. Alright, that's enough of that. Let's try 30 meter. So I'm unable to get this thing to tune on 30 meter for some reason. I don't know if it's because the properties of the ground here are different, or maybe because the radiator is elevated a little bit over there, but 30 meter is just not happening. I have been trying for the last 5 minutes here and I got nothing. If it won't tune, I'm not going to use it, so no point in doing that. I think, it's getting really wet. In fact, my KX2 is drenched now. I'm kind of worried about breaking it. For now, I'm going to pack up. I've got a lot of cleaning to do once I get back to the lab. So those are some pretty tough results. I thought that isolating the primary and secondary side would somehow allow the counterpoise to work as intended and that we would unlock the 30 to 40 meter band, but that appears to not be the case. Up until now, I thought that the antenna acted more like a end-fed random wire transformer with a built-in tuner, but that's looking less likely now. Now, while I was pondering this problem, there was just one question that was lingering in my head the whole time, which is, where the heck is this 5 watts of power going if it's not radiating out? Now, you might remember in the first video, I mentioned that I theorized that most of the current in the LC circuit would just circulate around and that some of it would radiate out. And I'm starting to think that perhaps, especially on the lower bands, that's very much the case, that all that current is just sitting there circulating in that LC circuit. So if that's true, that means most of our losses are really through core losses in that toroid. And if that's true, we should be able to see it with a thermal camera. So let's grab one of those and put that theory to test. And here's the test setup. I have the TinyGawant here mounted horizontally with the antenna fully deployed, and I've actually taken the back shell off so that we could look at the temperature of the components here using this thermal camera. So as we use the radio here to push 5 watts into it, we can actually see what are the hot components, where is all that energy really going. Now, I've dialed it to 7.03 megahertz, so 40 meter band, and I've got an SWR of about 1.4 to 1, which should be good enough. So I'm just going to move this over now to the KX2 and start testing and recording the temperature, and who knows what we'll see. We'll find out. All right, here we go, starting recording. So I'm going to start transmitting 5 watts and let's see what glows. Whoa! Holy, what? Shouldn't be much of a surprise, but man, that thing gets roasting hot. What? Oh, and that stays warm. All right, I just gotta try that again because that was way too cool. So I've let the toroid cool down a little bit. That's clearly the hot spot here. It seems like that toroid is completely saturating and heating up, but I want to run it one more time, make sure there was no fluke here, and also it's kind of cool to see the thing light up like a Christmas tree. Wow, watch, the SWR actually went from 2 to 1 to 3 to 1 and above as the toroid got warm, and we peaked at about 50 Celsius, so, you know, oh yeah, that thing is toasty. Let's try a different band. Let's go to the highest band now and see how it performs on 10 meter. All right, starting off at about 30 degrees Celsius on the max, so that'll be our starting temperature. 10 meter, here we go. Narrator Ara here. Quick note, in the 40 meter test, we saw a lot more uniformity in the heating because it was activating all the windings. Here in this test, you can actually see some asymmetry in the heating since the 10 meter band only uses 12 of the 25 turns on the toroid. Woo! We peaked at 60 Celsius. So that's where all the energy is going. Actually, it can't be all the energy, right? As I was recording this, I realized I've made a bunch of contacts with this antenna, so it does radiate. However, it looks and at least appears that much of the energy that we put into this antenna is going into that toroid. The question is how much, and really there isn't an easy way to test that here. But what I can do, just to sort of demonstrate the point of just because you have a good SWR doesn't mean you have a good antenna, I'd like to tune this up, show that it has a good match, and then take off the antenna to see what happens to our measurement. So I have the whip antenna here hooked up without a counterpoise and tuned to the 20 meter band, and we get about a 1.42 to 1 SWR. Now what happens when we take the antenna off? I'm keeping this in real time in case nobody believes me. Well, would you look at that? it shifted just a little bit in its resonant frequency, so adding this antenna does mess with this network here. But if I didn't tell you there was an antenna connected, you'd believe that there's a good antenna connected here and that you could transmit into it, but that doesn't mean it's going to radiate. This thing isn't going to radiate past this room here, let alone around the world. So that's a fun lesson. Just because you have a good SWR doesn't mean you have a good antenna. Go figure. With that said, this antenna does appear to be doing what I originally thought, where most of the current is actually circulating in that LC circuit. And while that's an inefficient antenna and that it barely radiates, it does actually work. Like, as you saw in the previous episode and in this episode, I'm able to make contacts with it on the higher bands. So this antenna does have a place in the ham radio world, and possibly in your kit. Now, I'd love to dive into the Rev C design, but this video is already very long and I did not intend for it to spiral out like this. I figured it would actually make more sense to stop here and to make the Rev C part a separate episode where I talk about taking all the final design improvements and essentially turning this thing into a product. I've thankfully gotten permission to use the name Gawant, so the TinyGawant name is going to stay, and I'll be able to produce these as kits for people to build and have fun with. But before we do that, and add the features like a gearbox and removing the 30 to 40 meter bands, and sort of improving the packaging so it's a little bit easier to use and more manufacturable, I need some beta testers. Now, one thing I haven't actually covered on this channel yet is the fact that I usually have beta testers who test beta products before the products see prime time. This helps me flesh out any issues I might have and to sort of polish it into a proper product that the final consumer will be happy with. So if you're interested in being a beta tester, please reach out to me at kits@n6ara.com. And I'm mostly going to be asking for feedback so that I can see if this antenna works with other people's setups and if there are any other problems I may have missed in my test coverage. Now keep in mind, I'm only going to be able to make maybe 20 or 30 of these kits, and they'll likely require some surface mount soldering. But I think folks who are savvy about building kits like this are probably going to take that on. And with that said, I just want to say thank you so much for watching. I cannot wait to make episode 3. And all the comments I've been getting have been just so positive, and folks have asked so many great questions. So if you have any questions and thoughts on this, feel free to drop them in the comments below. Don't forget to hit like and subscribe, and thank you all. 7-3. This is going to be all easily edited together, isn't it, Ara? No, it's not, Ara. I found a snowman friend. Should we give him a radio? We should give him a radio.